Yeah, so now we'll go into talk about Monte Carlo, which I think is super interesting by itself. I'm a little biased in that, but that's okay. So Monte Carlo simulation. So the reason why it's called Monte Carlo for us in the US and everything like that, it would have been called Las Vegas if it developed in the US. Basically, it's just the idea is that we're using randomness to do simulations. And so this is really useful because some simulations just make more sense to say, hey, like instead of doing every single possible change, we can essentially say, hey, let's randomly pick a lot about it and do it enough times where essentially we converge on the same answer as if we had done every single point and update it not randomly. So this can make it a lot more computationally efficient for simulations and calculations where you have to do this over and over and over again. So it can be super useful. So some code implementation from the curriculum kind of shows a little bit of like the classic of like Monte Carlo. So one thing you can do is do integration with Monte Carlo. So if you guys remember back from like what calculus really is in integrals, if you did an integral, basically have a function say, hey, what's the area underneath this curve? That is the integral. So you can actually say, well, okay, how would we do this? Well, one way you can do this is basically say, hey, let's just take the grid itself and throw a bunch of darts at it and see like where it lands. So I actually did this back when I was a science lab teacher with like Pi Day, March 14th. And what we did basically, you take basically a sheet right here. And the idea is if you throw darts randomly, right? So the key here is it's randomly. It'll either land on this, you know, let's say square size board, or it'll land like in this circle area. Actually, why am I drawing? I have drawing tools. I should use that. Okay, here we go. So you can imagine we had like a board like this. And then we had something like a circle, which this is my awful circle. Imagine it touching all the points. Okay. And then what we had like the little children do, and I had like people do this throughout the day. Basically, I actually had them like drop things, but because that was a little more random than people throwing it. But basically they would hopefully randomly land on parts on here. So you can see already there's a certain, it's gonna land more likely in this circle over like in these edges. But if we count out how many times we do this, like, oh, let's see, we did like, oh, we did 100 times, 100 little like dart throws. And we say how many came, how many actually landed within the circle, right? It's like, oh, okay, well, it turns out there was something like, you know, let's say this is like a size of like 1 by 1 or something like this. You say, oh, there's a certain proportion of this. Well, what's cool is that because this area here is in proportion to this square right here, this can actually tell you the area of this circle and basically say the likelihood of it landing here, assuming it's uniform. So this is essentially like how you can use randomness to essentially approximate without ever actually having to calculate any parts in this. Because computers actually are really bad at trying to find continuous values. It's much better at using discrete values where there's skipping over like 1, 2, or like making little dots and stuff like this. So it turns out this can be a lot more computationally efficient than trying to fill in this whole area. So what this looks like mathematically or computationally is we take some points. So in this case, I'm generating, let's see, 10,000. I think 10,000 should be fine. I make some uniform points, X and Y, right? And what I'm gonna do here basically is say, hey, inside the, in this here, I'm making a circle. So you can see the equation for a circle. Randomly distributed, how many times is basically does this land inside the circle? And I can basically count how many times this happens and I can plot this out. So what this looks like is essentially, is I randomly, that's uniform part, which is this X and Y. Essentially, I'm dropping those different points in there randomly on the grid. And I say, okay, look, I can see all the yellow ones that landed within the outside of the circle, and then inside the circle are these guys. And you can see this part. And what's cool is I can count up how much of the proportion of all these data points right here landed within the circle over the whole square itself. And so what's cool about that, I can then find the area of the circle inside there. So if I do this part, say how many landed inside, how many landed outside, you can actually get this part. In this case, I'm using the fraction sign versus total area. I can say print the total area of this guy, which if you look at the size of this thing is a radius of 1. And then, so if you guys remember the area of a circle, it's pi r squared. So it'd be pi times 1 squared, which is about 3.14. And you can see here, getting pretty close. It's not exact, but we wouldn't expect it to be exact, right? Because it would be random. But you can imagine if I did something like more and more points. In this case, it's not super optimized, so just know that this is why this runs a lot slower. There's a ways you can do this a little bit better. Excuse me. See this here, that's about 100,000. So that's probably why it's taking a little bit longer. But if I let this run, we'd have about 10,000 or 100,000 points landed honor points. And you can see it's taking a while. But you can imagine you could actually parallelize this And I know we haven't talked about parallelization in general yet, but you can think of it like, hey, have everyone like your computer, your computer, your computer, your computer, you drop like 100 points down here and say, okay, you drop 100 points over here. And then you combine them all together at the very end and we would get this full thing. So it makes it a little bit quicker. So you can see it ran for 32 seconds. And so we can see if I run this guy, it's a little bit closer to what the actual value of pi is. It's still off. I think it's 3.141. I don't know. I was a physicist. I didn't have to know past 1.4. So basically here, it's like, you know, it can get closer and closer. And as we increase the number of times we do this, we get closer and closer to that true value of pi. It turns out it's really slow, but you could do it. Cool. And that's how you can actually use randomness to determine something deterministic. And that's really what the whole point of Monte Carlo is. Cool. Any questions on like how this relates or any questions at all? Okay. So this is the classic example, which to be quite honest, I think is kind of boring. It's not really that exciting. It's like, oh, cool, you found the area of a circle. Fun. But this becomes really powerful when there are less obvious answers in like what you're trying to do. And that's where Monte Carlo simulations are super powerful. It's like, hey, there isn't a clear answer to this part. And when I say a clear answer, it's either one, it takes a lot of work. I'm like, I don't want to do a bunch of math. I got computers to do math for me. Like, let's just have the computer do the work. And that's what Monte Carlo can do. Or two, which is my favorite, is that you can't actually find the answer. There isn't a mathematical way to find the answer. And these are what we call it, I should say mathematical way. There's no closed form, which means you can't just write an equation and solve for x. So this is like a non-analytical solution. And those actually come up quite frequently where you're like, I don't know how to, like, there's no way for us to pull this answer out other than basically keep estimating closer and closer. So that's why Monte Carlo is really powerful because essentially you don't have to do it really close. You can just do it randomly. And I think that's the most amazing thing. So some examples of this. So some other resources. There's this great blog post right here that I have in this part of the curriculum. I don't know, has anyone looked at this by chance in the, from this notebook and everything? No? Okay, that's all right. So if you go into this guy right here, he talks about Monte Carlo and he goes through a whole bunch of different things, but he does have one where he talks about, what's it called? Different uses for Monte Carlo. So this can be useful for like weather prediction. It can be useful for other simulation games and stuff like this. So like, what do we expect things to go? Stock markets, like, well, what happens if we have similar, you know, for example, there's the Trinity study of saying, you know, what happens if you invest, you know, from 1920s and, you know, in different bond and like stock market, what would be the performance of it? And basically you can start determining a lot of different parts. My favorite one that he kind of does is, what if you had a drunk person try to go across the room and try to get into the bathroom? Like, what's the likelihood of them actually succeeding? And if you think about that, you know, in this case, like, oh, what do you mean by a drunk person? Well, what he basically describes is like, well, imagine this person who can randomly go in any direction, like, you know, turn around, go through. You can imagine a drunk person kind of walking around. You can see, looks kind of drunk, starting from this point right here, and see, can they actually get to this bathroom within a certain number of steps? And if you think about that, it's not super clear exactly what the answer is. You probably could mathematically reason this out over a long period of time, like, you know, probably figure it out and all these things, but it's like, hey, we got computers, let's just simulate it. So what you can do is basically simulate it over and over and over again. And so he actually has this GitHub repo, or it's actually, I didn't find the GitHub repo, I'm sure he has it, but he has a little walkthrough of this process. So essentially he writes this little simulation. You can walk through this yourself. I'm not gonna go through it. He's not using arbitrary data, but that's okay. Basically, he creates a walker episode and says, okay, let me just go ahead and see, like, you know, make this person who randomly chooses a path, you know, can turn 360 degrees and move any direction going forward kind of deal. I actually think he can turn 180 degrees, might not be 360. But the idea here is that he might randomly walk towards this direction, but he might always come off to the side and see if he can eventually get there. And then what he does, like, okay, we got this one time working. Let's try to do it many, many times. And basically he says, okay, let's try to do number of episodes. Basically how many, like, he gets a bunch of drunk people essentially, computationally, like not real, but like get some bunch of drunk people, say, hey, how many times do they actually make it to the bathroom? And you can see here, basically, not every single person is going to get there, but as we get more and more episodes, you actually see the average approach is a certain number. And you can actually say, oh, it's about, you know, 0.025. So at 2.5% of the time, they actually make it to the restroom based on these averages, or about 0.024. So, and you can see here there's many paths where he starts from this point and where he lands. So all these X's are the points where, like, he didn't quite make it to, or at least he didn't make it to this bathroom right here. So you can see basically 1 out of like maybe 50 that he would actually get into here. Okay, so this is where like you can solve like interesting problems that like don't really have a closed form, and you can do this. This is something you can do, for example, like if you wanted to see how often people are coming into the store. If you know the distribution or how the behavior of this, even if it's random. So you, for example, have a distribution, say, hey, what are people going to do? And then perform this Monte Carlo simulation over and over again. You can actually figure this answers out and say, hey, this is what we'd expect given these parameters and stuff like that. So it's a really useful tool that I think sometimes goes a little underutilized because it can be relatively easy to do, like in the sense of like, you know, perform this versus like trying to figure out mathematically or trying to, you know, pull out this information. We can use the distribution and say, hey, we can change this and create that simulation for us. Okay. Any questions on how this kind of, I don't know, any questions on Monte Carlo in general? Of anything I've talked so far? Cool. And the key point here is that we're using randomness. So like there's no like direct thing that we're saying, oh, we need to make this performance or this specific tool. We can basically use randomness. So there's one thing I can probably talk about then. Let's see if I can do this real quick. So one other part, which kind of similar to analytical, non-analytical solutions, I'll kind of show, I'm gonna flex and show off my my thesis. But let's see if I can pull this up real quick. So I have to pull it up from here. Where are you? There it is. Okay, well, that loads. So while I kind of let this load to show you talk about, one simulation I had done like for Monte Carlo that can be super useful is basically like for quantum mechanics. And so one thing, for example, these particles can basically have interactions with each other. So I have a little diagram here that makes it easy to kind of go through. So you imagine each of these little circles can affect each other and they either point up or they point down. And essentially they have a probability of flipping over up and down based on temperature and basically what their neighbors are. So it turns out if like, you know, all their neighbors are pointing up, they tend to want to point up as well. Or if they're antiferromatic, means they want to point in the opposite direction. So one thing you might want to say is like, well, okay, if we set the temperature, what's the likelihood of them all of a sudden flipping up so they're all kind of like pointing in the up direction? This is called like a phase change. And so it turns out if you have something like this is a square lattice, you can have something that they all tend to want to point in the same direction, or if they're next to each other, they want to flip each other over. Okay, and that's antiferromatic. It turns out there is no analytical solution for the antiferromatic triangular lattice. So this right here is a triangular or a square lattice. So you can see they tend to want to point up. And so it turns out you can see like how as temperature kind of increases, we have like this kind of change in the magnetization where they all tend to point up. So it's like them all pointing up, and this is when they tend to all kind of point in random directions. So there's this kind of this phase change right here where they tend to all want to point up, and then all of a sudden they're like, oh, I just want to go randomly. There's a certain temperature that happens right here. And you can actually mathematically show that it's like 2.269. Like you can actually find that exact answer. But it turns out some systems like the triangular lattice, where are you? There you are. So we have this kind of interaction. It's not really clear what they want to do. So they each have like two other neighbors essentially on this part. And so if this one points up and this one points down, if this one looks at this one here, it's like, oh, I want to point up as well. But then looks at this one, it's like, oh, wait, I want to point down. And so it doesn't really have a clear like what direction it should go. And it turns out there's no analytical solution for you to actually figure out what the value is supposed to be. So one thing you can do essentially is write a simulation. And so basically you can do say, hey, let me go ahead and try to change the temperature and see if there is a phase change that's going on here. And what's kind of cool about this, in my opinion, is that you don't actually have to go through, like you imagine like, if I show like this right here, you might think you have to go through every individual one. So this is the real big power of Monte Carlo. So there's still like probabilistic going through here, but you can imagine if I had like 100,000 little particles, I'd have to look at every individual particle before I say update one time. So I have to go each one, say, hey, what's your neighbor doing? Okay, you're gonna stay up. Oh, what's your neighbor's doing? Oh, you're gonna point down, and go through each one. So if 100,000, that would take a long time just to go through one iteration. And they say, okay, cool, that's one time step. Let's go ahead and do the next time step and do the whole thing over. Monte Carlo allows you to say, hey, let me just randomly pick the different points on here. So I pick this one, and I randomly pick this one, and I randomly pick this one, and update them randomly. And it turns out that this is actually relatively like computationally efficient, because I don't have to go through each individual one, but you'll still converge to the same answer, basically due to randomly going through here. So it makes it a lot more efficient. So you can basically make simulations that run, instead of having it run for like 4 hours, run it in like 10 minutes. And so you can even get more sufficient on that, or even quicker on that. So anyway, I thought this was a kind of a, obviously I'm a little biased because this is my project, but like I think it's a kind of a cool way for you to like see like what the power is, like what Monte Carlo can do. But as cool as that is, most people can't relate to quantum particles and stuff like that, because why would you, right? One thing is a little game. So Monte Carlo can be really useful for doing simulating games and what things are going to happen. And when I say games, that's just really saying certain set of behavior that's going to happen. So you imagine people coming into a store and say, how frequently are people coming in? And you can simulate this instead of just trying to observe what's happening. You can observe, say, what's the overall behavior, emulate that behavior in a simulation, and see what comes out. So this is a simple game of like, I call it like ultimate hopscotch. But basically there's these lines, you can kind of see these circles going on right here. And basically there's two teams of kids kind of going through, and they each can kind of just hop through each part. And then if they come across the other team, the other team's player, they have to do rock, paper, scissors. And you know, if you lose rock, you basically keep going until someone loses. And if someone loses, they have to run back to the beginning and start over. And then the next person kind of starts hopscotching across. And so the goal is basically to get all the way across. So you can imagine like, this can kind of go back and forth a little bit, especially if everyone's kind of equal like speed of hopscotching. So if you look at this, what this goes through, you can kind of see how this plays out. And so one question you might have, like honestly, like as a, like let's say this is a PE class, is how long is this game gonna go? Like, is this gonna take a long time? Like how many steps do I actually have to create? And so you can kind of see like, you know, for example, let's see if she actually wins this. So it looks like she keeps winning. But if she gets lost once, she has to go all the way back, and you can kind of say, hey, I was kind of curious when I saw this. I'm like, how long will this take? Like, how many steps do you have to actually do in order for you to actually get through here? Let's see if she actually wins. So there she has to restart. So you can see this game can go a long time, right? And it's random. So what I did over here was just go ahead and say, hey, let's run this simulation. So note that I didn't use object-oriented programming. In reality, you probably would like to use OOP, but this kind of quick way to kind of quickly check some stuff out. So I just wanted to show you guys a little bit of what this activity might look like, right? So if we run this like NumPy right here, get my imports, I basically created a couple of things. So one is basically one big mechanic in this game essentially says, hey, when two players come across each other, what happens, right? Like, well, they basically do a little battle, rock, paper, scissors. And that's the random part, right? And then whoever wins basically has to, or whoever loses has to go all the way back, and the other one keeps proceeding forward. So I basically wrote this little kind of guy right here. Say, hey, if, let's see here, if we're gonna battle, basically say who's gonna win, and then say, okay, that player resets or goes forward. This is a little helper function to help me decide how to do rock, paper, scissors, but you can find a whole bunch of ways you can determine the winner, right? But note this is gonna be that random part in here. And then say, okay, let's go ahead and say, this is kind of the main mechanic, and say, let's start off with, let's see here. Do I have this for going? Yeah. So you say, okay, let's go ahead and simulate this game. So in this case, I'm gonna say n steps, meaning there's n little circles for people to go through. And I'm having the players just walk one by one versus like, you know, different speeds. But you can imagine kind of tweaking this game and stuff like that, and differently, say what kind of like different speeds, or maybe sometimes they will go twice as fast. Other times some players might go, you know, slower and stuff like that. In this case, they're all the same speed. So what I'm gonna do here is say, okay, keep going through until basically either team 1 or team 2 reaches the opposite ends. And if they meet together, battle it out, and then have the other person restart and see what goes forward. So we can actually use this to kind of like get an idea of what's going on and actually simulate this game. So in this case, I have 9, and you can see here while this team goes through, I have a printout function here just for us to see what happens if we want to debug a little bit. Note one thing I didn't check for, because it was kind of like written relatively like quickly. I made a note that if there's an even number of n steps, there's a point where they can actually, like one's at 6 and one's at like 7, they can cross over hop over each other and the computer doesn't know any better. So I just keep it at odd, but this is something like you say, hey, check this out later. But I have this part right here. So if they're basically at the same position, should they battle it out? They go ahead and battle it out, and then they reset and they just keep going over and over and over and over again. So if we simulate this game now, and I'm going to go ahead and do a printout equals true. Oops, I have to actually run this guy. We can see a little bit of battle. So it's going to actually print out like what round it is and then where each person is, or which each player is at. So you can see here with only 9 parts, this is the first team, this is the second team. So they start out at 0 at 9. Then the next step is 1, 8, 2, 7, 3, 6, 4, 5, battle. So they don't have battle as part. And it looks like that team 2 lost that battle. So they have to go restart at 9. And you can see this going back and forth. In this case, turns out team 2 loses. And you can see going over and over and over again until it turns out about 57, 58 rounds. So you can kind of see like, okay, this is how long it would take each time. So it's like, all right, that's cool. But you can obviously think about like, well, if I run this again, right? Run this again. In this case, this is a much shorter one. It's about 30 rounds, right? So you can see that this might change a little bit on depending on what happens randomly, right? So when we can do this, say, hey, I want to know on average for like, let's say 9 steps, what this average is going to be. How long is this game going to last? Let's say I'm a PE teacher and say, hey, like how many games are we going to play in this game thing? Or how long can I expect this one game to go? So in this case, I'm going to run many, many games. So in this case, oh, did I skip over this? Oh yeah. So one thing I can do, so I just want to make sure I got this right. Yes, okay. So I'm going to run a simulation where basically, okay, I'm going to simulate the same game over and over and over and over again. But I want to say, hey, let's go ahead and, I'm kind of talking myself through. So, okay, I wrote a couple things. So this guy right here inside this for loop. So this for loop right here, this is going to run the same type of game with like 9 steps in there over and over 250 times. And this is going to give me an average, right? So I can run this over and over. Some games are going to have like 30 times, other times are going to be like 50, some can be more, some can be relatively quick, right? Where basically just go right across and always win every round. So I'm going to average that over. And then what I did in this bigger for loop here is saying, hey, let's not just see how long each individual game would work, but let's say we try doing it like, well, if there's 9 steps, what if there is 29, circles? What if there's like 39 circles? Let's go ahead and try this many, many times and see what that looks like. And this is the things like you could technically kind of pull this out with mathematics and try to figure out like, okay, is this going to be like, as we increase the size of it, will it go up like linearly? Will it kind of top out where we essentially have a short amount of rounds, or will it kind of go exponentially up higher and higher? So this allows us to basically plot these points out. So if I run this now, this is basically these different points right here are just showing if I had our very first one, which is basically 9 starts right here. The next one's going to be 29, and then it's going to be 39, 49, 59, and so on, is how many on average rounds that would take. So you can see here, I'm sorry, this is the different steps. So this is 59 circles, so 9 circles, 19 circles, 29 circles, and so on. And this right here is showing how many rounds on average this took, at least over 250. So you can see here, it's not actually a linear line right here. It actually turns out to be relatively kind of going up right here. It looks like it'd be exponential. And so this allows us basically to run this. And you can see it's like, oh, this is kind of nice. We can write it into a function, which I wrote here. So that's kind of like what this end simulations are. So I think I wrote this out of order. But you can see like, okay, let's build a function. And now we can run 9 simulations, for example. And we can see, for example, for 9 simulations on average after 150, it looks like, it's about 42. So you can see if I run this a little bit, it's going to be a little bit different, but it hovers around 40-ish, right? And so we can do this over for many, many parts. And so if I run this guy, I can do this and say, hey, what is this overall graph? And I can say, hey, let's say a round takes on average like 2 seconds. I can figure out how long each game is and figure out how many little circles do I need to actually put in there. And so you can see this actually could solve a problem. Now this is obviously a little kind of fun game, right? This doesn't have direct value, but you can see if you had something where a business case where you had people coming into a store and whatnot, you can actually kind of adjust and say, okay, well, how many people will come into this store based on these kind of random parameters. But this was relatively easy for us to understand. And you can see it kind of go through. Again, what's nice about these simulations, you can run them in parallel. So right here I had like about, you can see it took about 15 seconds, 16 seconds. to go from basically 20 different types. So it goes like 9, 19, 29, 39, 49, and so on. And you can see basically how many circles we need. This is like, took about 16 seconds. You can actually use parallel processing to essentially say, okay, in this case, it's just my one computer, but you could potentially do this on many different computers or many different, what they call threads, essentially different workers, and say, hey, you go ahead and simulate just 9 circles, you simulate 19 circles, you simulate 39 circles, and just tell me the answer afterwards. And this allows you to basically make it a little bit faster than using 16.8 seconds. It can be much quicker in this case. So that's the little thing I wrote here, but I won't run this because this will take a while and it won't, it'll kind of freeze up my computer because I'm obviously not using it for data science. But anyway, this is kind of like the idea here is like all I have to do is create basically like this simulate game part is saying what's the behavior going to happen, and just let me just go ahead and simulate that behavior and see on average what that would perform. And you can actually pull out information that would have been maybe a little bit harder for you to actually get. Okay. Cool. So that's kind of overall what I really wanted to share for Monte Carlo and like simulation, stuff like this. Do you guys have any overall questions or anything you guys would like to ask or all that?